Tonight, we're going to explore something you've probably never thought twice about: the fact that planets spin. Every world in our solar system rotates. But here's what's strange: they don't rotate the same way. Some spin incredibly fast, completing a day in just hours. Others take months to turn once. Some are tilted at crazy angles, rolling sideways through space. One planet even spins backward. And by the end of tonight, you're going to understand why this happens, what it tells us about the violent history of our solar system, and why figuring this out matters for finding life on other worlds. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about a merry-go-round. Once you get it spinning, it keeps spinning in the same direction at roughly the same speed until friction slows it down. That's conservation of angular momentum, one of the most fundamental principles in physics. An object in rotation tends to stay in rotation unless something acts on it. This principle applies everywhere in the universe, from spinning figure skaters to rotating galaxies. When a figure skater pulls their arms in, they spin faster. When they extend their arms, they slow down. The total angular momentum stays constant. Now apply this to planets. Every planet in our solar system is spinning. They've been spinning since they formed over 4.5 billion years ago. And once something that massive starts spinning, it doesn't just stop. There's no friction in space to slow them down. No air resistance. Nothing to break them. So they keep going, day after day, year after year, for billions of years. You'd think they'd all spin the same way, right? They all formed from the same rotating disk of gas and dust around the young sun. They should all be spinning in the same direction at similar speeds with similar tilts. But they don't. And that tells us something fascinating about the chaotic violence that shaped our solar system. Because rotation isn't something planets just decide to do. It's built into them from the moment they form. About 4.6 billion years ago, there was no sun, no planets, no solar system. Just a giant cloud of gas and dust floating in space. This cloud was massive, hundreds of times more massive than our current sun. It was also rotating, very slowly. Everything in the universe is rotating to some degree because of the chaotic motions of gas and matter. Even a tiny net rotation in a huge cloud becomes significant as the cloud collapses. And that's exactly what happened. Gravity started pulling the cloud inward. As it collapsed, it spun faster and faster. This is the same principle that makes figure skaters spin faster when they pull their arms in. As the radius decreases, the rotation rate increases to conserve angular momentum. The collapsing cloud flattened into a disk, with most of the mass concentrated in the center where the sun would form. The disk was rotating, and everything in it was moving in the same direction. This is why all the planets orbit the sun in the same direction. They all formed from the same rotating disk. And this is also why most planets rotate in the same direction as their orbits. They inherited that rotation from the disk material that built them. As dust particles in the disk collided and stuck together, they formed larger and larger objects. Pebbles, boulders, mile-sized planetesimals, 100-mile-sized protoplanets. Each collision added mass and angular momentum. If two objects collided head-on, their rotations might cancel out. But most collisions were glancing blows, hits from the side that added to the rotation. Over millions of years, these objects grew into planets, and their final rotation rates depended on the specific sequence of collisions they experienced. Every impact added or subtracted angular momentum, speed up or slow down the spin, tilt the axis one way or another. The planets we see today are the result of countless random collisions. No two planets experienced the same sequence of impacts, so no two planets ended up with the same rotation. This is the fundamental reason for the diversity we see: chaos, randomness, the unpredictable nature of collisions in the early solar system. Now, there are some patterns we can identify. The giant planets, Jupiter and Saturn, rotate very fast. This makes sense because they're massive and they formed quickly. They captured huge amounts of gas from the solar nebula before the sun's radiation blew it away. All that infalling gas was rotating, and it added to the planet's spin. By the time Jupiter and Saturn finished forming, they were spinning incredibly fast. And they've been spinning at roughly the same rate ever since. The ice giants, Uranus and Neptune, rotate a bit slower, but still quite fast. They're smaller than Jupiter and Saturn, but they still captured a lot of material, and their rotation rates reflect that. The rocky planets, Mercury, Venus, Earth, and Mars, are much smaller. They didn't capture gas from the nebula. They formed from solid material, rocky and metallic grains that stuck together over millions of years. Their rotation rates are generally slower because they didn't have that huge influx of rotating gas. But even among the rocky planets, there's huge variation. Earth and Mars have similar rotation rates, about 24 hours. But Mercury is locked in a resonance, and Venus spins backward incredibly slowly. These differences can't be explained just by formation. Something else happened to Mercury and Venus. Impacts, tidal forces, or both. Let's also talk about the role of moons. Moons form through several mechanisms. Some form in orbit around their planet from a disk of debris, similar to how planets form around the Sun. Others are captured asteroids or comets that were grabbed by the planet's gravity, and some form from giant impacts. Earth's moon formed when a Mars-sized object crashed into the early Earth. The impact vaporized part of Earth's mantle and the entire impactor. The debris went into orbit and eventually coalesced into the moon. This impact had a huge effect on Earth's rotation. Before the impact, Earth was probably rotating much faster, maybe every 5 or 6 hours. The impact transferred angular momentum to the debris disk and the moon. It also tilted Earth's axis. The moon has been slowing Earth's rotation ever since through tidal forces, and the moon stabilizes Earth's tilt, preventing it from wobbling wildly like Mars does. Without the moon, Earth's climate would be much less stable. The seasons would be chaotic. Life might not have evolved the same way, or at all. So the moon isn't just a pretty object in the night sky. It's a crucial part of Earth's habitability, and it's intimately connected to Earth's rotation. Other planets have moons too, and those moons affect their planets' rotations. Jupiter has 79 known moons. The 4 largest, the Galilean moons, have significant mass. They pull on Jupiter, creating tidal forces. But Jupiter is so massive that these forces barely affect its rotation. Jupiter has slowed down a tiny bit over billions of years, but the effect is small. Saturn has 82 known moons. Titan, the largest, is bigger than Mercury and has a thick atmosphere. Titan's gravity creates tides on Saturn, but again, the effect is small. Saturn's rotation has been remarkably stable. Uranus has 27 known moons, and Neptune has 14. These moons are smaller and have less effect on their planet's rotations. Mars has 2 tiny moons, Phobos and Deimos. They're probably captured asteroids, irregular in shape and only a few miles across. They have almost no effect on Mars's rotation. Mars is essentially rotating on its own, slowly wobbling over millions of years because there's no large moon to stabilize it. Mercury and Venus have no moons at all. Mercury is too close to the Sun. Any moon would be unstable and quickly pulled away by the Sun's gravity. Venus might have had a moon once, but it's gone now. Maybe it was destroyed in a collision, or maybe it spiraled into Venus due to tidal forces. We don't know. But the lack of a moon means Venus's rotation is entirely at the mercy of tidal forces from the Sun. Over billions of years, those forces have drastically slowed Venus's rotation and may have contributed to reversing it. So, moons matter. They stabilize rotations, slow them down through tidal forces, and provide clues about a planet's history. When we look at a planet's moons, we're also learning about the planet itself. Now, let's start with Earth, because it's the rotation we know best. Earth completes one full rotation in 24 hours. That's one day, the time it takes for the Sun to return to the same position in the sky. We've built our entire civilization around this rhythm. Our sleep cycles, our work schedules, our calendars, everything is based on Earth's 24-hour rotation. But here's something you might not realize. Earth's rotation is slowing down. Very slowly, but measurably. The Moon's gravity creates tidal bulges in Earth's oceans. These bulges drag across the ocean floor as Earth rotates beneath them, creating friction. This friction acts like a brake, very gradually slowing Earth's spin. We lose about 1.7 milliseconds per century. That sounds tiny, but it adds up over geological time. When dinosaurs walked the Earth 70 million years ago, a day was about 23.5 hours long. Go back further to the age of the earliest life, 3 billion years ago, and a day was only about 15 hours. Earth was spinning much faster then. In a billion years, assuming nothing catastrophic happens, a day on Earth will be about 25 hours long. And the Moon will be farther away, because the same process that slows Earth's rotation also pushes the Moon into a higher orbit. Right now, the Moon is drifting away from us at about 1.5 inches per year, roughly the rate your fingernails grow. Earth also has an axial tilt of about 23.5 degrees. This means Earth's axis isn't perpendicular to its orbit around the Sun. It's tilted. And this tilt is crucial. It's why we have seasons. When the northern hemisphere is tilted toward the Sun, it's summer there and winter in the southern hemisphere. 6 months later, the situation reverses. Without this tilt, we wouldn't have seasons. The equator would always be warm, the poles would always be cold, and the temperate zones would stay temperate year-round. Life on Earth would be completely different. So Earth's rotation seems pretty straightforward. 24-hour day, a mild tilt that gives us seasons, and a slow, gradual slowing over billions of years. But this is actually unusual. Most planets don't rotate like this. Take Mercury, the closest planet to the Sun. Mercury is strange. It's locked in what's called a 3-to-2 spin-orbit resonance. That means for every 2 orbits Mercury makes around the Sun, it rotates on its axis exactly 3 times. Mercury takes 88 Earth days to orbit the Sun. but it takes 59 Earth days to rotate once. This creates a bizarre situation. If you were standing on Mercury's surface, the time from one sunrise to the next, one solar day, would be 176 Earth days. That's 2 Mercury years for a single day-night cycle. The sun would crawl across the sky incredibly slowly, taking 88 days to go from sunrise to noon. And because of Mercury's elliptical orbit, the sun would actually appear to stop and move backward in the sky at certain points before continuing forward again. Imagine watching the sun rise, slowly climb toward the zenith, then reverse direction and go back toward the horizon before climbing again. It would be surreal. Why does Mercury rotate this way? Tidal forces from the sun. The sun's gravity is pulling on Mercury so strongly that over billions of years it has locked Mercury into this resonance. It's similar to how the moon is tidally locked to Earth. The same side of the moon always faces Earth because Earth's gravity has locked the moon's rotation to match its orbit. But Mercury isn't fully locked. It's in a 3-to-2 resonance instead of a 1-to-1 lock because of its elliptical orbit. The resonance is stable, and Mercury will likely stay in it for the rest of the solar system's existence. Now, let's talk about Venus, and this is where things get really weird. Venus spins backward. Every other major planet in the solar system rotates in the same direction, the direction the solar system formed in. This is called retrograde rotation. If you could look down on the solar system from above the sun's north pole, you'd see all the planets orbiting counterclockwise. And most of them are also spinning counterclockwise. Except Venus. Venus rotates clockwise. This is called retrograde rotation. And it's not just backward, it's also incredibly slow. Venus takes about 243 Earth days to complete one rotation. But it only takes about 225 Earth days to orbit the Sun. That means a day on Venus is longer than a year on Venus. Think about that. The planet completes an entire trip around the Sun before it finishes one spin on its axis. And because it's spinning backward, if you were standing on Venus's surface, assuming you could survive the hellish conditions, the sun would rise in the west and set in the east. The opposite of every other planet. Why does Venus spin this way? Nobody knows for certain. The leading theory is that Venus was hit by a massive object early in its history. An asteroid or a small planet that struck with enough force to flip Venus's rotation or drastically slow it down. Computer simulations show that a collision at the right angle and speed could have reversed Venus's spin. Another possibility is gravitational interactions with the Sun and Venus's thick atmosphere. Venus's atmosphere is incredibly dense, about 90 times thicker than Earth's. The Sun's gravity pulls on this thick atmosphere, creating atmospheric tides. Over billions of years, these tides could have slowed Venus's rotation and eventually reversed it. But this explanation has problems. The timescales involved are longer than the age of the solar system. So the collision theory is favored, but we can't be certain. We don't have a smoking gun, no crater or debris field that definitively proves a massive impact. Venus is also nearly untilted. Its axial tilt is only about 2.6 degrees, almost perfectly upright. This means Venus has essentially no seasons. The sun stays at nearly the same angle in the sky year-round. Not that it matters much, because Venus's surface is a scorching 470 degrees Celsius or 878 degrees Fahrenheit everywhere, day and night, poles and equator. The thick carbon dioxide atmosphere traps heat so efficiently that temperature variations are minimal. Mars is more normal. Mars rotates in the same direction as Earth and takes about 24 hours and 37 minutes to complete one rotation. A Martian day, called a sol, is only slightly longer than an Earth day. This similarity is one reason Mars is considered a good candidate for human colonization. Our circadian rhythms, our natural sleep-wake cycles, are roughly 24 hours. We could adapt to Mars's day length relatively easily. Mars also has a tilt of about 25 degrees, very similar to Earth's 23.5 degrees. This means Mars has seasons just like Earth. Martian summers and winters, spring and fall. But because Mars's orbit is more elliptical than Earth's, the seasons are more extreme and unequal. The southern hemisphere's summer is shorter and hotter than the northern hemisphere's summer because Mars is closer to the sun during the southern summer. The northern hemisphere's summer is longer and milder. These seasonal changes drive the growth and retreat of Mars's polar ice caps. In winter, carbon dioxide freezes out of the atmosphere and falls as dry ice snow, building up the polar caps. In summer, the dry ice sublimates back into gas, shrinking the caps. This seasonal cycle creates winds and weather patterns across the planet. But Mars's rotation hasn't always been stable. Mars has no large moon to stabilize its tilt. Earth's moon acts like a gyroscope, keeping Earth's tilt relatively constant at about 23.5 degrees. This stability is part of why Earth's climate has been relatively stable over billions of years, allowing life to evolve and thrive. Mars doesn't have that. Its two tiny moons, Phobos and Deimos, are too small to provide any stabilizing effect. Computer models show that Mars's tilt has varied wildly over millions of years, swinging from as low as 0 degrees to as high as 60 degrees. When Mars's tilt was higher, the poles would have received much more direct sunlight during summer. This could have melted ice and released water vapor into the atmosphere, creating a thicker atmosphere and possibly even liquid water on the surface. Then the tilt would decrease, the climate would cool, and Mars would freeze again. This chaotic wobbling may explain some of the geological features we see on Mars today. Evidence of ancient rivers and lakes that came and went as the climate oscillated. Right now, Mars's tilt is similar to Earth's, and it's been relatively stable for the past few million years. But that's temporary. In a few million years, it will shift again. Now, we get to the gas giants, and this is where rotation gets really interesting. Jupiter is the fastest rotating planet in the solar system. It completes one full rotation in just under 10 hours. 9 hours, 55 minutes, and 30 seconds to be precise. For a planet that's 11 times wider than Earth, that's astonishingly fast. Jupiter's equator is moving at a speed of about 28,000 miles per hour. Compare that to Earth's equatorial speed of about 1,038 miles per hour. Jupiter is spinning so fast that it bulges at the equator. The equator is about 7% wider than the distance from pole to pole. You can see this in pictures of Jupiter. It's not a perfect sphere, it's an oblate spheroid, squashed at the poles and bulging at the equator. This rapid rotation drives Jupiter's weather. The fast spin creates strong Coriolis forces, which organize the atmosphere into distinct bands of clouds running parallel to the equator. These are the light zones and dark belts you see in images of Jupiter. The zones are regions of rising gas, where ammonia ice condenses into white clouds. The belts are regions of sinking gas, where the atmosphere is clearer and you can see deeper, darker layers. The boundaries between these bands are where the winds are strongest. Jupiter's winds can reach speeds of over 385 miles per hour, far faster than any hurricane on Earth. And these winds have been blowing for as long as we've been observing Jupiter, centuries at least, possibly billions of years. The Great Red Spot, Jupiter's famous storm, has been raging for at least 350 years. It's a high-pressure system larger than Earth, rotating counterclockwise in Jupiter's southern hemisphere. It's powered by Jupiter's internal heat and the planet's rapid rotation. But why does Jupiter spin so fast? It has to do with how Jupiter formed. Jupiter formed from the collapsing cloud of gas and dust that surrounded the young sun. As this cloud collapsed under its own gravity, it spun faster and faster, just like a figure skater pulling in their arms. The conservation of angular momentum. Most of this spinning material ended up in the sun, but some of it formed a disk around the sun, and from that disk, the planets formed. Jupiter, being massive, captured a huge amount of material from the disk, and all that material was already rotating. As it fell onto the growing planet, it added to Jupiter's spin. The more material Jupiter captured, the faster it spun. By the time Jupiter finished forming, it was spinning incredibly fast. And since there's no friction in space to slow it down, it's still spinning at roughly the same rate today. Jupiter's tilt is only about 3 degrees, almost perfectly upright. This means Jupiter has essentially no seasons. The sun shines on the equator year-round with very little variation. The poles remain in perpetual twilight. Saturn is similar to Jupiter in many ways. It's also a gas giant, though smaller, about 9 times wider than Earth. It rotates quickly, though not as fast as Jupiter. Saturn completes one rotation in about 10 hours and 39 minutes. Like Jupiter, Saturn is spinning fast enough that it bulges at the equator. In fact, Saturn's bulge is even more pronounced than Jupiter's. Saturn is the least dense planet in the solar system. It's made mostly of hydrogen and helium, the lightest elements. If you could find an ocean big enough, Saturn would float. This low density means Saturn is more easily deformed by its own rotation. The equator is about 10% wider than the pole-to-pole distance. Saturn's rapid rotation also drives its banded cloud patterns, similar to Jupiter's, though less distinct because Saturn's atmosphere is hazier. There's a thick layer of photochemical smog in the upper atmosphere that obscures the deeper layers. But the same physics applies. Fast rotation creates Coriolis forces, organizing the atmosphere into zones and belts with high-speed winds at the boundaries. Saturn's winds are even faster than Jupiter's, reaching speeds of over 1,100 miles per hour, near the equator. At Saturn's North Pole, there's a bizarre feature called the hexagon, a massive jet stream flowing in the shape of a perfect hexagon about 18,640 miles across. Each side of the hexagon is wider than Earth. It was discovered by the Voyager spacecraft in the 1980s and confirmed by the Cassini mission. The hexagon has been stable for decades, possibly much longer. We don't fully understand why it forms a hexagon instead of a circle or some other shape. It has to do with the interaction between Saturn's rapid rotation and the jet stream, but the exact dynamics are complex. Saturn's tilt is about 26.7 degrees, similar to Earth's. This means Saturn has seasons. Each season lasts about 7 years, because Saturn takes 29.5 Earth years to orbit the Sun. The seasons affect Saturn's atmosphere, changing the colors and intensity of the cloud bands. They also affect the rings. The rings appear to tilt toward or away from us as Saturn moves through its orbit. When the rings are edge-on, they almost disappear because they're incredibly thin, only about 10 meters thick in most places. When they're tilted, they're spectacular, reflecting sunlight and casting shadows on the planet. Uranus is the strangest planet in terms of rotation. Uranus is tipped over on its side. Its axial tilt is about 98 degrees. Most planets spin like tops, their axes more or less perpendicular to their orbital plane. Earth tilts at 23.5 degrees. Saturn at 26.7 degrees. Even Jupiter at 3 degrees. But Uranus is lying on its side, rolling around the Sun like a barrel. This creates bizarre seasonal patterns. During Uranus's summer in the northern hemisphere, the North Pole points almost directly at the Sun and stays in continuous sunlight for 42 Earth years. The South Pole is in complete darkness for the same period. Then, as Uranus continues its orbit, the seasons shift. Eventually, the South Pole points toward the Sun and gets 42 years of continuous daylight, while the North Pole freezes in darkness. The equator experiences day and night cycles, but the Sun rises and sets at strange angles, sometimes almost overhead, other times skimming along the horizon. Why is Uranus tipped over like this? The almost certain answer is a collision. Early in the solar system's history, when planets were still forming and migrating, Uranus was likely struck by an Earth-sized object or possibly multiple smaller objects. The impact was so violent that it knocked Uranus onto its side. Computer simulations show that a collision with an object about 1 to 3 times Earth's mass could have tilted Uranus to its current orientation. The collision would have been cataclysmic. It likely vaporized the impactor and stripped away some of Uranus's atmosphere. But Uranus survived, and it's been rolling through space ever since. Interestingly, Uranus's moons orbit around its equator, not around the solar system's plane. This suggests the moons formed after the collision from the debris disk left behind. Or they were captured, and their orbits were reshaped by the collision. Uranus rotates relatively quickly, taking about 17 hours and 14 minutes to complete one rotation. But because of its extreme tilt, the definition of a day on Uranus gets complicated. Do you measure from sunrise to sunrise? That depends on where you are on the planet and what time of year it is. At the poles, the sun doesn't rise and set. It just circles around the horizon during the long summer, then disappears for the long winter. Neptune is similar to Uranus in size and composition, but its rotation is more normal. Neptune's axial tilt is about 28.3 degrees, similar to Earth and Saturn. This gives Neptune seasons, though they're very long because Neptune takes 165 Earth years to orbit the Sun. Each season lasts about 40 years. Neptune rotates quickly, taking about 16 hours and 6 minutes to complete one rotation. This rapid rotation drives powerful winds in Neptune's atmosphere. Neptune has the fastest winds in the solar system, even faster than Jupiter's or Saturn's. Winds near Neptune's equator blow at speeds of over 1,200 miles per hour. Why Neptune has such fast winds is a mystery. Neptune receives very little energy from the Sun because it's so far away, about 30 times farther from the Sun than Earth. The sunlight that reaches Neptune is about 900 times weaker than the sunlight hitting Earth. Yet Neptune's atmosphere is incredibly active. There are massive storm systems, including one called the Great Dark Spot, similar to Jupiter's Great Red Spot. The Great Dark Spot was observed by Voyager 2 inches 1989, but when the Hubble Space Telescope looked at Neptune a few years later, the spot had disappeared. New spots have appeared and disappeared since then. Neptune's atmospheric activity is driven by internal heat. Neptune radiates about 2.6 times more heat into space than it receives from the Sun. This internal heat comes from the slow contraction of the planet under its own gravity, and possibly from chemical reactions in the deep atmosphere. This heat powers the winds and storms, creating one of the most dynamic atmospheres in the solar system despite being so far from the Sun. So we have 8 planets with wildly different rotations. Mercury, locked in a strange resonance. Venus spinning backward, slower than it orbits. Earth, with a nice 24-hour day and a stabilizing moon. Mars, similar to Earth, but with a wobbling tilt. Jupiter and Saturn, spinning incredibly fast, completing a day in about 10 hours. Uranus tipped on its side, rolling through space. Neptune, with extreme winds, despite being so far from the Sun. Why are they all so different? The answer is chaos. The solar system formed from a rotating disk of gas and dust about 4.6 billion years ago. This disk was spinning, so everything that formed from it inherited some of that rotational motion. All the planets should have started with prograde rotation, spinning in the same direction as the disk. But the early solar system was violent. There were thousands of planetesimals, protoplanets, and smaller bodies all orbiting the Sun. They were constantly colliding, merging, and scattering each other. Every collision changed the rotation of the objects involved. A glancing blow might speed up a planet's rotation or slow it down. A head-on collision might reverse it entirely or tilt its axis. The planets we see today are the survivors of this chaotic period. Their rotations are the result of countless impacts over millions of years. Venus's backward rotation, Uranus's sideways tilt, Earth's 23.5-degree tilt. These are all scars from the violent birth of the solar system. We can model this with computer simulations. Scientists run thousands of simulations of the early solar system, varying the initial conditions slightly each time. The number of planetesimals, their sizes, their orbits, all randomized within plausible ranges. Then, they let the simulation run, watching as the planetesimals collide and merge over millions of simulated years. The results show that almost every simulation produces planets with different rotations. Some fast, some slow, some tilted, some backward. The specific outcome depends on the random sequence of collisions, which is unpredictable. Earth could easily have ended up like Venus, spinning backward, or like Uranus, tipped on its side. We got lucky. The particular sequence of impacts that Earth experienced left us with a stable rotation and a large moon that stabilizes our tilt. That stability was crucial for the development of life. If Earth's tilt had varied wildly like Mars's, the climate would have been chaotic. Ice ages and hot periods would have come and gone unpredictably. Life would have had a much harder time gaining a foothold. The moon also creates tides, which may have been important for early life. Tidal pools, the mixing of nutrients, the cycling of water, all driven by the moon's gravity. So, Earth's rotation isn't just a random quirk. It's a key part of why we're here. And this brings us to exoplanets, planets orbiting other stars. We've discovered over 5,000 exoplanets so far. Most of them are nothing like the planets in our solar system. There are hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. There are super-Earths, rocky planets several times more massive than Earth. There are ice giants, lava worlds, water worlds, planets we can barely categorize. And their rotations are just as diverse as their other properties. Many exoplanets are tidally locked to their stars. This means one side always faces the star, baked in perpetual daylight, while the other side is in eternal darkness. This is common for planets orbiting close to their stars. The star's gravity is so strong that over time it locks the planet's rotation to match its orbit, the same way the moon is locked to Earth. If you were on the day side of a tidally locked planet, the star would hang motionless in the sky, never rising or setting. The day side would be scorching hot, possibly hot enough to vaporize rock. The night side would be freezing cold, possibly cold enough to freeze the atmosphere solid. The only habitable zone might be the terminator, the boundary between day and night, where the star sits permanently on the horizon. Here, the temperature might be moderate enough for liquid water. But the climate would be strange, with constant winds rushing from the hot day side to the cold night side. Some tidally locked planets might have thick atmospheres that redistribute heat from the day side to the night side, creating more stable temperatures across the planet. These worlds might be habitable despite the extreme conditions. We don't know yet. We've only just begun to study exoplanet atmospheres. Other exoplanets might be spinning incredibly fast, faster than Jupiter. If a planet formed from a rapidly rotating disk and didn't experience many collisions, it could retain a very high rotation rate. A day might last only a few hours. The planet would bulge dramatically at the equator, and the Coriolis forces would create extreme weather patterns. Or an exoplanet might be tipped at an extreme angle, even more extreme than Uranus. A planet with a 180-degree tilt would be completely upside down, spinning backward like Venus, but also inverted. Every collision, every close encounter with another planet, every interaction with its star can change an exoplanet's rotation. The diversity we see in our own solar system is probably just a small sample of what's possible. Understanding planetary rotation matters for more than just curiosity. It has practical implications for finding habitable worlds. A planet's rotation affects its climate. Fast rotation, like Earth's or Mars's, creates day-night cycles that distribute heat around the planet. This prevents extreme temperature differences and creates more stable conditions. The planet heats up during the day and cools at night, but the cycle is short enough that temperatures don't reach extremes. The atmosphere and oceans circulate, moving heat from the day side to the night side. This creates weather patterns, winds, ocean currents, all driven by the rotation. On Earth, the rotation creates the Coriolis effect, which causes hurricanes to spin and jet streams to flow west to east. These circulation patterns are crucial for distributing heat and moisture around the planet. Without rotation, Earth's climate would be completely different. The day side would bake, while the night side froze. There would be no hurricanes, no jet streams, no global circulation patterns. Just a simple convection cell, with rising air on the day side and sinking air on the night side. Slow rotation, or tidal locking, creates extreme temperature differences between the day side and night side. On a tidally locked planet, one hemisphere permanently faces the star. That side gets blasted with constant radiation, heating up to extreme temperatures. The other side never sees the star, cooling down to frigid temperatures. The only potentially habitable zone might be the terminator, the boundary between day and night. Here, the star sits permanently on the horizon. Temperatures might be moderate, not too hot, not too cold, but the climate would be strange. Constant twilight, with the star never rising or setting. Winds rushing from the hot day side to the cold night side, creating perpetual storms. Some models suggest that a thick atmosphere could redistribute heat and make tidally locked planets habitable. The atmosphere would carry heat from the day side to the night side, evening out the temperatures. This could create a stable climate despite the lack of rotation. But we don't know for sure. We've only just begun to study the atmospheres of exoplanets. We'll need more observations to understand whether tidally locked worlds can support life. A planet's axial tilt affects its seasons. Earth's 23.5-degree tilt creates seasons that are predictable and regular. Winter, spring, summer, fall, each lasting about 3 months. This seasonal variation drives climate patterns. Snow falls in winter, melts in spring. Plants grow in summer, die back in fall. Animals migrate, hibernate, or change behavior with the seasons. Ocean currents shift. Atmospheric circulation changes. The whole planet responds to the tilt-driven seasons. And life has adapted to these seasonal cycles. Many organisms have internal clocks that track the seasons. They know when to breed, when to migrate, when to store food for winter. These adaptations are fundamental to how ecosystems work. A planet with no tilt would have no seasons. Just constant conditions at each latitude. The equator would always be warm, the poles always cold. There would be no seasonal migration, no hibernation, no leaves changing color in fall. Life would be more static, less dynamic. Not necessarily worse, just different. Some organisms might thrive without seasonal stress, but the lack of seasonal variation would fundamentally change how ecosystems evolve. A planet with an extreme tilt, like Uranus, would have bizarre seasons. 42 years of continuous sunlight at the pole, then 42 years of darkness. The temperature swings would be enormous. In summer, the pole would heat up as the sun circles the sky for decades. In winter, it would freeze as the sun disappears for decades. Few organisms could survive such extremes. Maybe deep underground, where temperatures are more stable. Maybe in the oceans, where water moderates temperature changes. But the surface would be harsh, alternating between baking heat and freezing cold. It's hard to imagine complex life evolving on a world like that. A planet's rotation also affects its magnetic field. This is crucial for habitability. Earth's magnetic field is generated by the motion of molten iron in the outer core. This motion is driven partly by Earth's rotation and partly by convection currents in the liquid metal. The combination creates a dynamo effect, turning Earth into a giant electromagnet. the magnetic field extends far into space, creating a protective bubble called the magnetosphere. This magnetosphere deflects the solar wind, a stream of charged particles flowing from the sun. Without the magnetosphere, the solar wind would hit Earth's atmosphere directly. Over time, it would strip away the atmosphere, carrying it off into space. This is what happened to Mars. Mars once had a thick atmosphere and liquid water on its surface. But Mars's core cooled and solidified, shutting down the magnetic field. Without the field, the solar wind stripped away most of the atmosphere. Now Mars has only a thin atmosphere, about 1% as thick as Earth's, and there's no liquid water on the surface. Mars is a cold, dry, barren world, in part because it lost its magnetic field. A planet with a very slow rotation might not generate a strong magnetic field. The dynamo effect depends on rapid motion of conducting fluids in the core. If the planet spins too slowly, the motion might not be fast enough to generate a field. Venus rotates incredibly slowly, and it has almost no magnetic field. This might be part of the reason. Venus's core might be solid, or it might not be rotating fast enough to drive a dynamo. We don't know for sure because we can't see inside Venus. But the lack of a magnetic field means Venus's atmosphere is exposed to the solar wind. Interestingly, Venus has kept its thick atmosphere despite this. The atmosphere is so thick and heavy that the solar wind can't strip it away easily. But over billions of years, Venus has lost lighter gases like hydrogen. A tidally locked planet might not have any magnetic field at all. If the planet isn't rotating, or rotating very slowly, there might not be enough internal motion to drive a dynamo. This could leave the planet vulnerable to atmospheric loss and radiation. However, some tidally locked planets might have magnetic fields generated by other mechanisms. Tidal heating from the star could drive convection in the core, or interactions with a moon could generate internal motion. We're still learning how magnetic fields work on different types of planets. So, when we search for habitable exoplanets, we need to consider rotation. Not just the planet's size, mass, and distance from its star, but also how fast it spins, what direction it spins, and how tilted it is. All of these factors affect habitability. A fast-rotating planet with a moderate tilt and a strong magnetic field is more likely to support life. It will have stable temperatures, predictable seasons, and protection from stellar radiation. A slowly rotating or tidally locked planet with an extreme tilt and no magnetic field is less likely to be habitable. It will have extreme temperature variations, chaotic or non-existent seasons, and exposure to harmful radiation. Of course, life is adaptable. We find life in extreme environments on Earth. Organisms living in boiling hot springs, frozen Antarctic lakes, deep underground, high in the atmosphere. Life finds a way. So maybe life could exist on a tidally locked planet or a planet with an extreme tilt. We just don't know yet. But rotation gives us one more data point to consider when evaluating exoplanets for habitability. There's also the question of how to measure exoplanet rotation. We can't directly observe most exoplanets. They're too far away and too faint. We detect them indirectly by watching for tiny dips in a star's brightness as the planet passes in front of it, or by measuring the wobble in the star's motion caused by the planet's gravity. These methods tell us the planet's size, mass, and orbital period, but they don't tell us how fast the planet is spinning. measuring rotation requires more sophisticated techniques. One method is to study the planet's atmosphere. If the planet has clouds or storms that move across its surface, we can track them to determine the rotation rate. This requires observing the planet over time and detecting changes in its brightness or spectrum. Another method is to measure the Doppler shift in the light reflected from different parts of the planet. If the planet is rotating, one side is moving toward us and the other side is moving away. This creates a measurable shift in the spectrum. These techniques are incredibly difficult. They require powerful telescopes and careful observations. But we're starting to do it. We've measured the rotation rates of a few exoplanets, mostly hot Jupiters. As our technology improves, we'll be able to measure more, and that will give us a much better understanding of how planets form and evolve. There's something almost poetic about planetary rotation. These worlds are spinning in the darkness of space. Some fast, some slow, some tilted, some backward. Each rotation is a story, a record of the impacts and interactions that shaped that world. Every planet is different because every planet had a different history. And when you look up at the night sky and see a planet, Venus or Mars or Jupiter, remember that it's spinning. Right now, as you watch, it's turning. Clouds are swirling across its atmosphere, driven by that rotation. Storms are forming and dissipating. Seasons are slowly changing. The planet is a dynamic, active world, not just a point of light. And the way it spins tells us about its past, its present, and possibly its future. Because rotation isn't static. It changes over time. Earth's rotation is slowing. Mars's tilt is wobbling. Even Jupiter and Saturn's rotations are slowly evolving as they lose tiny amounts of angular momentum to their moons. Billions of years from now, the solar system will look different. Earth's day might be 25 or 26 hours long. The moon might be even farther away. Mars's tilt might have shifted to a completely different angle. Venus might still be spinning backward, or maybe another impact will flip it back. We don't know. The future is as chaotic and unpredictable as the past. But we can study it, model it, try to understand the forces at work. And that's what makes planetary science so fascinating. We're detectives, piecing together the history of the solar system from the clues left behind. The rotation rates, the tilts, the moons, the scars of ancient impacts. Every piece of data tells us something. Let's also consider what rotation means for human exploration. If we ever send humans to other planets, rotation will matter. On Mars, the day is almost the same length as Earth's. Astronauts could follow a normal sleep-wake cycle. They could grow plants in greenhouses that follow the Martian day. They could work during the day and rest at night, just like on Earth. But on Mercury, where the day lasts 176 Earth days, the situation is completely different. You can't just wait for nightfall to cool down. Nightfall won't come for months. Any base on Mercury would need to be mobile, constantly moving to stay in the Terminator region, where the sun is low on the horizon and temperatures are more moderate. Or it would need to be underground, insulated from the extreme surface temperatures. On Venus, the slow backward rotation creates a day that lasts 243 Earth days. But you wouldn't see the sun anyway, because the thick clouds block all direct sunlight. The surface is in perpetual dim twilight, lit only by diffused light scattered through the atmosphere. On Jupiter or Saturn, There is no surface. They're gas giants. But if we sent floating platforms into their atmospheres, those platforms would need to deal with the extreme rotation. The winds would be fierce, and the Coriolis forces would make navigation challenging. On Uranus, the extreme tilt creates bizarre lighting conditions. During the long polar summer, the sun circles around the sky, but never sets. During the long polar winter, it's dark for decades. Any human presence would need to adapt to these extreme seasonal cycles. Rotation matters. It affects everything, from the length of the day to the climate to the weather to the habitability. And understanding it is crucial for planning any kind of presence on another world. We're also learning that rotation can be a window into a planet's interior. A planet's rotation rate can tell us about its internal structure. Earth's rotation is affected by the distribution of mass inside the planet. The core, the mantle, the crust, all rotating together but with slightly different properties. By measuring tiny variations in Earth's rotation, scientists can infer properties of the deep interior. For example, the inner core rotates slightly faster than the rest of the planet. We know this because seismic waves traveling through the core show a small Doppler shift that changes over time. This tells us about the coupling between the inner core and the outer core. Similarly, by measuring changes in Earth's rotation rate over time, we can learn about the motion of fluids in the outer core and the mantle. This helps us understand the geodynamo that generates Earth's magnetic field. The same principles apply to other planets. If we can measure a planet's rotation precisely enough, we can infer details about its interior. Is it solid or liquid? Is it differentiated into layers? Is there a core? These are fundamental questions about planetary structure, and rotation is one of the tools we use to answer them. There's also the matter of resonances. Mercury is locked in a 3:2 resonance with the Sun. Some moons are locked in resonances with their planets. Io, Europa, and Ganymede, 3 of Jupiter's large moons, are locked in a resonance called the Laplace resonance. For every 1 orbit Ganymede makes, Europa makes 2, and Io makes 4. This resonance is stable and keeps the moons aligned in a specific pattern. The gravitational tugs between the moons maintain the resonance and also pump energy into Io's interior, creating the most volcanically active body in the solar system. Resonances are common in the solar system. They're a natural consequence of gravitational interactions over long timescales. When 2 bodies orbit with periods that are simple ratios of each other, they can fall into a resonance. Once in a resonance, the system is often stable for billions of years. Resonances can also be disruptive. They can eject objects from stable orbits or prevent objects from settling into certain regions. The Kirkwood gaps in the asteroid belt are caused by resonances with Jupiter. Asteroids that orbit at certain distances from the Sun have periods that are simple ratios of Jupiter's period. Jupiter's gravity gives them a periodic tug that builds up over time, eventually ejecting them from that orbit. This creates gaps in the asteroid belt where few asteroids remain. Understanding resonances is crucial for understanding the long-term evolution of planetary systems. And rotation can be affected by resonances too. Mercury's rotation is a resonance. Tidal forces can lock planets and moons into rotational resonances with their parent bodies. These resonances shape the architecture of planetary systems. Let's talk about what happens when rotation goes wrong. Or rather, what happens when something disrupts a planet's rotation. We've talked about impacts that can tilt a planet or reverse its spin. But there are other mechanisms too. Gravitational interactions with other planets can change rotation over time. If two planets pass close to each other, the gravitational tug can alter their spins. This doesn't happen in our solar system anymore because the planets are in stable orbits. But in the early solar system, when planets were migrating and orbits were more chaotic, close encounters were common. Each encounter could change a planet's rotation slightly. Over millions of years, these small changes could add up to significant alterations. There's also the possibility of a planet losing its atmosphere, which can affect rotation. The atmosphere adds mass and angular momentum to the planet. If the atmosphere is stripped away by solar wind or a catastrophic impact, the planet's rotation could speed up slightly. Conversely, if a planet accretes a thick atmosphere from comet impacts or volcanic outgassing, the rotation could slow down. These effects are small, but they're real. And over billions of years, small effects can have large consequences. One of the most interesting questions is whether life can affect rotation. On Earth, life has not significantly changed our rotation rate. The biosphere is too small compared to the mass of the planet. But life has affected the atmosphere, which in turn affects climate and weather patterns. Could life on another planet affect rotation? It's hard to imagine how. Life doesn't exert torque on the planet directly. But life could theoretically alter the atmosphere in ways that affect atmospheric tides, which could then affect rotation over geological timescales. This is highly speculative, but it's an interesting thought. If we found a planet with an unusual rotation rate that couldn't be explained by impacts or gravitational interactions, could that be a sign of life? Probably not, but it's worth considering all possibilities. There's also the philosophical angle. The fact that every planet rotates differently reminds us that the universe is not uniform. Every world is unique, shaped by its own history. This diversity is part of what makes the solar system and the universe so fascinating. If all planets rotated the same way, if they all had the same day length and the same tilt, the universe would be boring. The diversity of rotations mirrors the diversity of everything else. Sizes, compositions, atmospheres, surfaces, climates, all different. And that diversity is a consequence of the chaotic processes that formed and shaped the planets. The early solar system was a violent place. Planetesimals colliding, merging, shattering. Protoplanets migrating inward and outward, scattering smaller bodies. Gravitational interactions, flinging objects into new orbits. Out of this chaos, order emerged. Stable orbits, distinct planets, regular patterns. But the scars of the chaos remain. The rotations are those scars. Each planet's spin is a record of the impacts it endured. And when we study those rotations, we're reading the history of the solar system. Let's talk more about the early solar system and how planetary migration affected rotation. Because the planets didn't always orbit where they do now. In the first few 100 million years after the solar system formed, the planets were migrating, moving inward or outward from their original orbits. This migration was driven by interactions with the disk of gas and dust that still surrounded the Sun. As a planet orbits through a disk, it creates gravitational disturbances. These disturbances create spiral density waves in the disk, similar to the spiral arms of a galaxy. These waves exert a gravitational tug on the planet. The tug from the outer part of the disk pulls the planet outward. The tug from the inner part pulls it inward. Which way the planet moves depends on the density and distribution of material in the disk. For massive planets like Jupiter, the interaction is strong enough to carve a gap in the disk. Jupiter literally pushes material away from its orbit, creating an empty lane. But material is still flowing across this gap, and it tugs on Jupiter. The net effect is that Jupiter migrates, usually inward toward the Sun. This is called Type 2 migration, and it's thought to be slow but steady. Over millions of years, Jupiter could have moved inward significantly. In fact, some models suggest that Jupiter formed much farther out than it is now, maybe at 5 or 6 AU, instead of its current 5.2 AU. Then, it migrated inward, moving closer to the Sun. But something stopped it. Most likely, Saturn formed and started migrating inward as well. When Jupiter and Saturn got into a specific orbital configuration, a 2-to-1 resonance where Saturn orbits twice for every one orbit of Jupiter, something strange happened. The two planets started pushing each other back outward. This is called the Grand Tack hypothesis. Jupiter tacked, like a sailboat changing direction, and moved back outward. This migration had huge consequences for the rest of the solar system. As Jupiter moved inward, it scattered asteroids and planetesimals. Some were thrown into the inner solar system, bombarding the rocky planets. Others were ejected from the solar system entirely. Jupiter's migration may have prevented a planet from forming in the asteroid belt. The region between Mars and Jupiter should have formed a planet, but the material there is too scattered. Maybe Jupiter's migration stirred things up too much, preventing the material from coalescing. When Jupiter moved back outward during the Grand Tack, it scattered more objects. Some of these may have impacted the inner planets, including Earth. The Late Heavy Bombardment, a period about 4 billion years ago when the inner planets were heavily bombarded, might have been caused by Jupiter's migration. And all of this affected planetary rotation. Every impact changes rotation. A large asteroid slamming into a planet can speed up its rotation, slow it down, or tilt its axis. The Grand Tack may have been responsible for some of the rotation anomalies we see today. Maybe the impact that reversed Venus's rotation happened during this period. Maybe the impact that tilted Uranus occurred as the giant planets were migrating. We don't know for sure, but the timing is suggestive. The early solar system was chaotic, and migration made it even more chaotic. Uranus and Neptune probably didn't form where they are now. They likely formed closer to Jupiter and Saturn, maybe at 7 or 8 AU. Then they were scattered outward by gravitational interactions with Jupiter and Saturn. This scattering process was violent. Uranus and Neptune would have encountered thousands of smaller objects as they moved outward. Each encounter changed their orbits slightly. And some encounters could have been violent enough to affect their rotations. The impact that tilted Uranus probably happened during this migration phase. A large object, maybe an Earth-sized protoplanet, struck Uranus as it was being scattered outward. The collision knocked Uranus onto its side. Neptune might have had close encounters too, but none violent enough to tilt it dramatically. Or maybe Neptune was hit by multiple smaller objects that partially cancelled out. We don't know. But the point is, planetary migration and rotation are connected. Migration increases the chances of collisions. Collisions change rotation. The rotations we see today are partly the result of migration in the early solar system. This has implications for exoplanets too. We've discovered many exoplanets that are very close to their stars. Hot Jupiters orbiting in just a few days. These planets clearly didn't form where they are now. Gas giants can't form that close to a star because it's too hot. All the gas would have been blown away by the star's radiation. So these hot Jupiters must have formed farther out and then migrated inward. And during that migration, they probably experienced collisions and close encounters that affected their rotation. Some hot Jupiters are tidally locked, which makes sense if they've been close to their stars for a long time. But some are not fully locked, suggesting they migrated inward relatively recently. Or they experienced an impact that kicked them out of tidal lock. The diversity of exoplanet rotations reflects the diversity of migration histories. Some planets migrated smoothly, others had violent journeys. Each journey left its mark on the rotation. We're learning that planetary systems are dynamic, not static. Planets move, collide, scatter each other. Rotation is part of this dynamic story. There's also the question of retrograde rotation in exoplanets. We've found a few exoplanets that appear to be rotating backward relative to their orbit, just like Venus. But even more extreme, some are orbiting backward. These are called retrograde orbits. The planet goes around the star in the opposite direction from the star's rotation. How does this happen? One possibility is a close encounter with another planet. If two planets pass very close to each other, the gravitational interaction can flip one of them into a retrograde orbit. This is rare, but it can happen. Another possibility is the Kozai mechanism. If a planet has a distant companion, either another planet or a star, that companion can gradually tilt the planet's orbit through gravitational interactions. Over millions of years, the orbit can be tilted more and more until it flips over completely into a retrograde orbit. Once the planet is in a retrograde orbit, tidal forces from the star can affect its rotation. The planet might end up rotating backward too. So retrograde rotation isn't unique to Venus. It's a phenomenon that can occur in any planetary system with the right conditions. And it tells us about the violent, chaotic history of that system. Now let's think about what rotation tells us about a planet's interior. Because rotation isn't just about the surface. It's about the entire planet, from the core to the atmosphere. When a planet rotates, different layers may rotate at different rates. Earth's inner core rotates slightly faster than the rest of the planet. We know this from seismic waves that pass through the core. The waves show a small Doppler shift that changes over time, indicating the core is rotating faster. Why does the core rotate faster? It's complicated, involving the interaction between the solid inner core and the liquid outer core. The outer core is flowing, generating Earth's magnetic field. This flow couples to the inner core and can drag it along, making it rotate faster. But the effect is small, maybe 1 degree per year faster than the surface. Over millions of years, the inner core has rotated ahead of the surface by a measurable amount. Understanding this helps us understand the dynamics of Earth's interior, how the core and mantle interact, how heat flows through the planet, how the magnetic field is generated. All of this is connected to rotation. For other planets, we can infer interior properties from their rotation too. Jupiter's rotation is not uniform. Different latitudes rotate at different speeds. The equator rotates faster than the poles. This is called differential rotation, and it's common in gas giants. There's no solid surface to enforce uniform rotation. The atmosphere is fluid, and different parts can rotate independently. By measuring the rotation at different latitudes, we can learn about Jupiter's internal structure. How deep does the atmosphere go before you hit something solid, or at least much denser? Is there a solid core? Or is Jupiter gas all the way down? These questions are still being debated. NASA's Juno spacecraft, orbiting Jupiter since 2016, has been measuring the planet's gravitational field. These measurements give us clues about the interior, and they're related to rotation. A rotating planet bulges at the equator, and the amount of bulge depends on the internal structure. A planet with a solid core bulges differently than a planet without one. By measuring the bulge and combining it with rotation data, we can infer what's inside. It's like using rotation as an X-ray to see inside the planet. The same technique works for exoplanets. If we can measure an exoplanet's rotation and its shape, we can infer its internal structure. Does it have a solid core? Is it differentiated into layers? Is the interior hot or cold? All of these questions can potentially be answered by studying rotation. Let's also consider how rotation connects to a planet's formation chemistry. When planets form, they accrete material from the surrounding disk. This material has different compositions depending on where it comes from. Close to the Sun, it's too hot for ice to exist. Only rocky and metallic grains can condense. So the inner planets, Mercury, Venus, Earth, and Mars, are made mostly of rock and metal. Farther out, beyond the frost line, at about 3 to 4 AU, ice can condense. This is where the giant planets formed. Jupiter and Saturn are made mostly of hydrogen and helium, the lightest and most abundant elements. But they also contain ices, water, ammonia, methane in their deep interiors. Uranus and Neptune are even richer in ices. They're called ice giants because ices make up a large fraction of their mass. The composition affects rotation. A planet made of dense rock and metal will rotate differently than a planet made of lightweight gas. Density affects how mass is distributed, which affects angular momentum. A denser planet can spin faster without flying apart. A less dense planet has a lower limit on how fast it can spin. Saturn is a perfect example. Saturn is the least dense planet, made mostly of hydrogen and helium. It's spinning so fast that it's bulging dramatically at the equator. If Saturn spun much faster, it would start to tear itself apart. The centrifugal force at the equator would overcome gravity, and material would fly off into space. Saturn is close to this limit. It's spinning about as fast as it can without disintegrating. Jupiter is denser and can spin faster, but it's also close to its limit. The rocky planets are much denser and could theoretically spin much faster. But they don't, because they didn't accrete as much rotating material as the gas giants. So composition and rotation are linked. The material a planet is made of affects how fast it can spin, and the amount of material it accretes affects how much angular momentum it has. Both factors combine to determine the final rotation rate. There's another fascinating aspect of rotation we haven't fully explored yet. Precession. Precession is a slow wobble in a planet's axis of rotation. Earth's axis precesses, completing one full wobble every 26,000 years. This means the North Celestial Pole, the point in the sky that Earth's axis points toward, slowly moves relative to the stars. Right now, Earth's axis points toward Polaris, the North Star. But 5,000 years ago, it pointed toward a different star, Thuban. In another 5,000 years, it will point toward yet another star. This precession is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. Earth is not a perfect sphere. It bulges at the equator because of its rotation. The Sun and Moon pull on this bulge, creating a torque that causes Earth's axis to wobble. Precession has been known since ancient times. The Greek astronomer Hipparchus discovered it in the 2nd century BC by comparing old star catalogues with his own observations. He noticed that the positions of stars had shifted slightly over hundreds of years. This shift is caused by the slow wobble of Earth's axis. Precession affects the seasons. The time of year when Earth is closest to the Sun, called perihelion, slowly shifts because of precession. Right now, perihelion occurs in early January, during Northern Hemisphere winter. But in 10,000 years, perihelion will occur in July, during Northern Hemisphere summer. This will make Northern Hemisphere summers slightly warmer and winters slightly colder. The effect is small, but it's real and measurable. Mars also precesses, but its precession is much more chaotic than Earth's. Mars has no large moon to stabilize its axis. So, the precession is driven by the Sun and the gravitational tugs of Jupiter and Saturn. These tugs vary as the planets move in their orbits, causing Mars's axis to wobble unpredictably. Sometimes Mars's tilt is 25 degrees, like now. Sometimes it's as low as 10 degrees or as high as 60 degrees. These large swings in tilt have dramatic effects on Mars's climate. When the tilt is high, the poles get more sunlight, melting ice and releasing gas into the atmosphere. When the tilt is low, the poles freeze and the atmosphere thins. This chaotic precession may explain why Mars's climate has been so variable over its history. Evidence of ancient rivers and lakes suggests Mars once had liquid water. But the climate changed, the water froze, and Mars became the cold desert we see today. Maybe the tilt was higher in the past, creating a warmer climate. Then, the tilt decreased, the climate cooled, and the water disappeared. Understanding precession helps us understand the long-term climate evolution of planets. It's another piece of the rotation puzzle. There's also the phenomenon of true polar wander. This is when the solid outer layer of a planet, the crust and mantle, rotates relative to the core. It's different from precession, which is a wobble of the rotation axis. True polar wander is a physical rotation of the entire outer shell. Earth has experienced true polar wander several times in its history. We know this from paleomagnetic data, measurements of ancient magnetic fields preserved in rocks. These measurements show that the magnetic poles have been in different locations at different times, not just wandering around as they do now, but actually flipping to completely different positions. This suggests that Earth's outer layer rotated relative to the core. Why would this happen? It's related to mass distribution. If a large mass anomaly forms in the crust or mantle, like a huge volcanic province or a dense metallic deposit, it creates an imbalance. The planet's rotation tries to stabilize this imbalance by rotating the mass toward the equator. Over millions of years, the entire outer layer can rotate to bring the mass anomaly to the equator. This is true polar wander. It's a slow process, taking tens of millions of years, but it can have significant effects on climate. If the continents rotate to different latitudes, ocean currents change, wind patterns shift, and the climate evolves. True polar wander may have contributed to some of Earth's ice ages and warming periods. Mars may have experienced true polar wander too. The Tharsis volcanic region, a massive bulge on Mars's surface containing several giant volcanoes, is located near the equator. Some scientists think Tharsis formed elsewhere, and then Mars's outer layer rotated to bring it to the equator. This would explain why Tharsis is where it is. The rotation wanted to put the heavy mass at the equator, so the planet obliged. True polar wander connects rotation to geology and climate. It's yet another way that rotation affects the evolution of planets. Now, let's talk about asteroids and their rotations. Because it's not just planets that spin. Every object in the solar system is rotating. Asteroids, comets, moons, even small rocks floating in space. And their rotations tell us about their histories. Most asteroids are tumbling chaotically through space. They're not spinning smoothly around a single axis like planets. They're wobbling and tumbling because they're irregularly shaped and they've been knocked around by collisions. When two asteroids collide, the impact transfers angular momentum. The asteroids start spinning, or their spins change. If the asteroid is oddly shaped, the spin is unstable and it tumbles. Some asteroids are spinning incredibly fast. There are asteroids that complete one rotation in just a few minutes. These are called fast rotators. They're typically small, less than a few hundred meters across, and they're held together by their own strength, not by gravity. Gravity would be too weak to hold such a small object together if it was spinning that fast. The centrifugal force would tear it apart. So fast rotating asteroids must be solid chunks of rock or metal, strong enough to withstand the centrifugal force. Other asteroids are spinning much more slowly. Large asteroids, hundreds of miles across, typically rotate every few hours to a few tens of hours. This is similar to planetary rotation rates. And it makes sense because larger asteroids are more like mini-planets. They have enough gravity to pull themselves into roughly spherical shapes. They're spinning because they accreted from smaller objects that were already rotating. Some asteroids are actually binary systems. Two asteroids orbiting each other. The two asteroids are tidally locked, with one side always facing the other. They orbit their common center of mass, and they rotate at the same rate they orbit. Just like the Moon is tidally locked to Earth. These binary asteroids formed when a single asteroid was spun up to the point where it split into two pieces. Or they formed when two asteroids had a gentle collision and got captured into orbit around each other. Binary asteroids are fairly common, especially among near-Earth asteroids, and their rotations tell us about how asteroids interact and evolve. Comets also rotate, but their rotations are harder to measure. Comets develop tails when they get close to the Sun. The Sun's heat vaporizes ice on the comet's surface, creating jets of gas and dust. These jets shoot out from the nucleus, the solid core of the comet. And the direction of the jets depends on which part of the nucleus is facing the Sun. As the nucleus rotates, the jets sweep around, creating spiral patterns in the tail. By watching these patterns, we can determine the comet's rotation period. Most comets rotate every few hours to a few tens of hours. But some comets have very slow rotations or very fast rotations. And some comets are tumbling chaotically, their rotation axes wobbling all over the place. This chaotic tumbling is usually caused by the jets themselves. As gas shoots out from the nucleus, it creates a reaction force, like a rocket engine. This force can change the comet's rotation. If the jets are not symmetrically placed, they create a torque that makes the comet tumble. Over time, the comet's rotation becomes more and more chaotic. Eventually, the comet might split apart if the rotation becomes too extreme. We've observed several comets fragmenting as they approach the Sun. The combination of solar heating and rotational stress tears them apart. So, rotation affects even small objects like comets. It's a universal phenomenon, driven by the same physics that governs planets. Let's also think about how rotation affects space missions. When we send spacecraft to other planets, we have to account for their rotation. Landing on a rotating planet is tricky. You have to time your descent so that you land in the right place. Mars rotates in about 24.5 hours. So, if you're descending toward Mars, the landing site is moving underneath you. You have to adjust your trajectory constantly to hit the target. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance all had to navigate this problem. They entered the Martian atmosphere, traveling at thousands of miles per hour. Then, they used parachutes and rockets to slow down, all while the surface rotated beneath them. The descent took about 7 minutes, and during that time, Mars rotated about 3 degrees. That doesn't sound like much, but at the landing site, it's several miles of motion. The spacecraft's navigation system had to account for this rotation to land precisely. And it worked. All 4 rovers landed within their target zones. For planets that rotate faster, like Jupiter or Saturn, the problem is even worse. These planets rotate in about 10 hours, so the surface is moving much faster. If we ever send a probe into Jupiter's atmosphere, it will have to deal with wind speeds of hundreds of miles per hour, all driven by the planet's fast rotation. The probe would be buffeted by powerful storms and jet streams, making navigation extremely difficult. We've sent probes into Jupiter's atmosphere before. The Galileo probe in 1995 descended into Jupiter, measuring temperature, pressure, and wind speed. It lasted for about an hour before being crushed by the increasing pressure. During that hour, it experienced winds of over 385 miles per hour, all caused by Jupiter's rotation. Future probes will have to be even more robust if we want to explore deeper into the atmosphere. For tidally locked planets, landing is easier in some ways. The same side always faces the star, so you don't have to worry about rotation during descent. But the extreme temperatures on the day side and night side create other challenges. You'd probably want to land on the terminator, the boundary between day and night. Here, temperatures are more moderate. But the winds are fierce because air is constantly rushing from the hot day side to the cold night side. Any lander would have to deal with these winds. So, rotation affects mission planning in practical ways. It's not just an abstract concept. It's something engineers have to account for when designing spacecraft and planning trajectories. But perhaps the most profound question about rotation is how it relates to life. Could life exist on a planet that rotates very differently from Earth? What about a tidally locked world? where one side Yonyan faces its star, or a planet like Uranus, rolling on its side with bizarre seasonal patterns? Let's explore these questions because they're central to the search for life beyond Earth. Earth's rotation creates a 24-hour day-night cycle. This cycle is fundamental to life as we know it. Organisms have evolved circadian rhythms, internal biological clocks that track the day-night cycle. Plants open their leaves during the day to photosynthesize and close them at night. Animals have sleep-wake cycles tied to daylight. Even single-celled organisms show circadian rhythms, their metabolism speeding up during the day and slowing at night. These rhythms are deeply embedded in the biology of Earth's life. They're controlled by genes that regulate when certain proteins are produced. And they're remarkably precise, often matching the 24-hour cycle to within minutes. But here's the interesting part. The circadian clock is not exactly 24 hours. In most organisms, it's slightly longer or slightly shorter. For humans, it's about 24 hours and 11 minutes on average. The clock has to be reset every day by exposure to sunlight. Without sunlight, the clock drifts, and people's sleep schedules gradually shift. This suggests that the circadian clock evolved to track Earth's rotation. It's been fine-tuned by billions of years of evolution to match our planet's day-night cycle. Now, imagine a planet that rotates much faster or much slower. Could life evolve there? And if it did, would it have circadian rhythms? On a planet that rotates every 10 hours, like Jupiter, life would experience very short days and nights. 5 hours of light, 5 hours of darkness. Any organisms that photosynthesize would need to adapt to this rapid cycle. Maybe they'd be more efficient at photosynthesis, capturing as much energy as possible during the short day. Or maybe they'd store energy during the day to use at night. On a planet that rotates every 100 hours, life would face the opposite problem. 50 hours of continuous sunlight, then 50 hours of darkness. Photosynthetic organisms might overheat during the long day if they can't dissipate the energy fast enough. And they'd starve during the long night unless they could store enough energy to last. But life is adaptable. We find organisms in extreme environments on Earth. Bacteria living in hot springs at temperatures near boiling. Microbes living in frozen Antarctic ice. Organisms living deep underground with no access to sunlight. Life finds a way to survive in almost any condition. So maybe life could adapt to different rotation rates. The organisms might look different and function differently than Earth life, but they could still exist. The real challenge is tidal locking. On a tidally locked planet, there is no day-night cycle. One side always faces the star in perpetual daylight. The other side never sees the star in permanent darkness. This creates extreme temperature differences. The day side gets roasted by constant stellar radiation. Temperatures could be hundreds of degrees Celsius. Any water would evaporate, and the atmosphere on the day side might be stripped away by the star's radiation. The night side freezes. Without sunlight, temperatures could drop to -200 degrees Celsius or lower. Any water would be frozen solid. The atmosphere might even freeze out as solid nitrogen or oxygen snow. At first glance, a tidally locked planet seems uninhabitable. But there's a middle ground, the terminator, the boundary between the day side and night side. Here, the star sits permanently on the horizon. It's perpetual dawn or dusk, depending on your perspective. Temperatures at the terminator might be moderate. Not too hot, not too cold. Maybe just right for liquid water. This is called the terminator, habitability zone, and it's where life might exist on a tidally locked planet. But the conditions would be strange. The star would never move in the sky. It would just sit there, on the horizon, unchanging. There would be no seasons, no day-night cycle, no variation, just constant twilight. The only changes would be driven by atmospheric circulation, winds blowing from the hot day side to the cold night side. These winds could be incredibly strong, creating perpetual storms. The atmosphere would be in constant motion, trying to redistribute heat. Hot air, rising on the day side, flowing toward the night side, cooling and sinking, then flowing back. This circulation could create habitable conditions across a wider area than just the terminator. If the atmosphere is thick enough, it could transport heat from the day side to the night side effectively. This would moderate temperatures on both hemispheres. The day side wouldn't be quite as hot, and the night side wouldn't be quite as cold. Maybe the entire planet could be habitable, not just the terminator. Computer models of tidally locked planets suggest this is possible. If the planet has an atmosphere as thick as Venus's, heat transport could keep both hemispheres at habitable temperatures. Water could exist on the day side without boiling away, and the night side wouldn't freeze completely. But there's a catch. A thick atmosphere like Venus's would create a runaway greenhouse effect. Temperatures would be extreme, hundreds of degrees, far too hot for life. So there's a balance. The atmosphere needs to be thick enough to transport heat, but not so thick that it traps too much heat. Finding this balance is tricky, and it depends on many factors. The distance from the star, the composition of the atmosphere, the presence of clouds, the amount of water on the surface. All of these affect whether a tidally locked planet can be habitable. We're discovering many tidally locked exoplanets. Most planets orbiting red dwarf stars are tidally locked. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They're small, cool, and long-lived, burning for trillions of years. But they're also dim. For a planet to be warm enough for liquid water, it has to orbit very close to a red dwarf. Close that tidal forces lock the planet's rotation to its orbit. This means that the majority of potentially habitable exoplanets might be tidally locked. And if that's the case, we need to understand whether life can exist on tidally locked worlds. Because if it can't, the number of habitable planets in the galaxy drops dramatically. But if it can, then tidally locked planets might be common homes for life. We just don't know yet. We need more observations, more models, and maybe eventually, direct detection of life on a tidally locked exoplanet. There's also the question of what life on a tidally locked planet would look like. Would it be similar to Earth, life, or completely different? On Earth, life is powered by the sun. Plants photosynthesize, converting sunlight into chemical energy. Animals eat plants or other animals, ultimately deriving their energy from the sun. Even organisms living in the deep ocean or underground often rely on organic matter that originated from photosynthesis at the surface. On a tidally locked planet, the sun doesn't rise and set. On the day side, it's always there, shining brightly. Photosynthesis would be continuous, not cyclic. Plants might grow faster because they have access to constant sunlight. Or they might overheat and need mechanisms to cool down. Maybe they'd evolve reflective surfaces to bounce back excess light. Or maybe they'd develop ways to store energy for periods when conditions are unfavorable. On the night side, there's no sunlight. But there might be other energy sources. Geothermal energy from volcanic activity, chemical energy from reactions between rocks and water, even bioluminescence, organisms creating their own light. Life on Earth has adapted to dark environments, like deep-sea hydrothermal vents. Here, organisms don't rely on sunlight. They use chemical energy from the vent fluids, a process called chemosynthesis. Bacteria convert hydrogen sulfide or methane into energy, and other organisms feed on these bacteria. Entire ecosystems exist in complete darkness, powered by chemistry, not sunlight. Maybe the night side of a tidally locked planet could support similar ecosystems. Organisms clustered around volcanic vents or geothermal hotspots. Or maybe life would be confined to the Terminator, where conditions are most Earth-like. We won't know until we find it. And that's one of the most exciting frontiers in astrobiology, searching for life on worlds that are completely unlike Earth. Now let's consider what rotation means for the future of humanity in space. If we ever become a spacefaring civilization, we'll need to adapt to different rotation rates. Living on Mars would be relatively easy from a rotation perspective. The day is only 40 minutes longer than Earth's. Astronauts could maintain a roughly 24-hour schedule. They'd adjust their clocks slightly, and their circadian rhythms would adapt. Studies of people living in isolation chambers with non-24-hour day-night cycles show that humans can adapt to days as short as 23 hours or as long as 25 hours without too much difficulty. Beyond that range, it gets harder. On Mercury, where the day lasts 176 Earth days, maintaining a normal sleep schedule would be impossible. Humans would need to create artificial day-night cycles using lights and dark periods. Underground habitats would probably be necessary anyway to escape the extreme surface temperatures. And inside those habitats, you could impose a 24-hour cycle regardless of what the sun is doing outside. On the gas giants' moons, like Europa or Titan, the day length is determined by the moon's rotation. Europa is tidally locked to Jupiter, so one side always faces Jupiter. A day on Europa, from Jupiter rise to Jupiter rise, is about 3.5 Earth days. Titan is tidally locked to Saturn with a rotation period of about 16 Earth days. Living on these moons, humans would need artificial lighting to create a normal day-night cycle. And the psychological effects of not seeing a normal sun or having a normal sky would be significant. But humans are adaptable. We've lived in extreme environments on Earth, from polar regions with months of continuous daylight or darkness, to submarines and space stations where day and night are completely artificial. We can create our own rhythms if the natural ones don't suit us. The bigger challenge might be on planets with extreme tilts. On Uranus, the seasons last decades. 42 years of continuous sunlight at the pole, then 42 years of darkness. Building a colony that could survive both extremes would be difficult. You'd need massive energy storage to get through the long night. Solar panels would work during the summer, but not the winter. Nuclear power or geothermal energy would be essential. And the colonists would need to endure psychological challenges of living in darkness for decades. Maybe colonization of such worlds is impractical. Or maybe future technology will make it feasible. We don't know yet, because we're still in the early stages of becoming a spacefaring species. But rotation will definitely be a factor in where and how we expand into the solar system. There's also the possibility of changing a planet's rotation. Could we speed up or slow down a planet's spin? Deliberately, not through natural processes. This sounds like science fiction, but it's worth considering. If we wanted to terraform Mars, making it more Earth-like, we might want to adjust its rotation. Mars's day is already close to Earth's, so that's not necessary. But we might want to stabilize Mars's axial tilt to prevent the wild climate swings that happen over millions of years. One way to do this would be to give Mars a large moon, a moon massive enough to stabilize the tilt through tidal forces. But creating or capturing a moon is far beyond our current technology. We'd need to redirect a large asteroid or even a dwarf planet into orbit around Mars. The energy required would be enormous, and the risks would be huge. If the object came in too fast, it would crash into Mars. If it came in too slow, it wouldn't be captured. Getting it just right would require precision we don't have yet. Another idea is to use massive impacts to change rotation. A large asteroid slamming into a planet can change its rotation rate or tilt. If we could control where and how the asteroid hits, we might be able to adjust the rotation deliberately. But again, this is incredibly dangerous. A large impact could devastate the planet's surface, destroying any existing ecosystems or colonies. The risks far outweigh the benefits, at least with our current technology. More realistically, we might be able to adjust the rotation of small bodies like asteroids. If we're mining an asteroid and want to change its rotation for easier access, we could use rockets or mass drivers. Attach engines to the asteroid and fire them in a specific direction to change the spin, or eject material from the asteroid's surface to create a reaction force. This has been proposed as a way to deflect dangerous asteroids that might hit Earth. Change the asteroid's rotation or orbit so it misses Earth. We haven't done it yet, but the technology is within reach. In the far future, advanced civilizations might have the capability to adjust planetary rotations. But for now, it remains in the realm of speculation and science fiction. Let's also think about the aesthetic and philosophical dimensions of rotation. There's something beautiful about the fact that every planet spins differently. It's a reminder that the universe is not uniform or predictable. Each world has its own character, its own rhythm, its own history. When you look at the planets, you're seeing the results of billions of years of chaos and order, collisions and migrations, random chance and physical law. And all of it is encoded in the rotation. The way a planet spins tells a story. Mercury's 3:2 resonance speaks of tidal forces and gravitational locks. Venus's backward rotation hints at a catastrophic impact. Earth's stable 24-hour spin reflects the stabilizing influence of the Moon. Mars's wobbling tilt shows the consequences of having no large moon. Jupiter's rapid spin reveals the massive accretion of gas during formation. Uranus's sideways tilt is a scar from a violent collision. Every rotation is a clue, a piece of evidence in the cosmic detective story. And we're learning to read these clues, to piece together the history of the solar system from the spins of its planets. This work is ongoing. Every new mission, every new observation adds to our understanding. The Juno spacecraft has measured Jupiter's gravitational field with unprecedented precision, revealing details about the planet's interior and rotation. The Cassini mission spent 13 years at Saturn, studying its rotation, its rings, its moons. The New Horizons flyby of Pluto in 2015 gave us our first close-up look at a dwarf planet's rotation. Pluto and its moon Charon are tidally locked to each other, always showing the same faces. They orbit their common center of mass like a dumbbell spinning in space. It's a unique configuration, different from anything else in the solar system, and it tells us about how Pluto and Charon formed and evolved. Future missions will continue this exploration. NASA's Europa Clipper will study Jupiter's moon Europa, including its rotation and tidal flexing. The Dragonfly mission will send a drone to Titan, Saturn's largest moon, exploring its surface and studying how it rotates. These missions will add more pieces to the puzzle. So what have we learned tonight? Planets rotate, but they all rotate differently. Mercury is locked in a strange resonance, taking 59 days to spin once and 88 days to orbit the Sun. Venus rotates backward, taking 243 days to complete one rotation, longer than its year. Earth rotates every 24 hours with a stabilizing moon that keeps our tilt constant. Mars rotates in about 24.5 hours, but has a wildly wobbling tilt. Jupiter rotates in less than 10 hours, the fastest rotation in the solar system, driving powerful storms and winds. Saturn also rotates in about 10 hours, creating a hexagonal jet stream at its north pole. Uranus is tipped on its side, rolling through space with its axis nearly in the plane of its orbit. Neptune rotates in about 16 hours and has the fastest winds in the solar system, despite being so far from the Sun. These differences are not random. They're the result of the violent, chaotic history of the solar system. Impacts that tilted planets, slowed them down, or flipped them over. Gravitational interactions that locked planets into resonances or altered their spins. The accretion of material that spun planets up as they formed, and the ongoing processes that continue to change rotation rates over time. Tidal forces slowing Earth's rotation and pushing the Moon away. Atmospheric tides affecting Venus. Gravitational interactions between planets and moons. Understanding planetary rotation helps us understand how planets form and evolve. It helps us predict the climates of exoplanets and assess their habitability. It gives us insight into the internal structure of planets. And it reminds us that every world is unique, shaped by its own history. When you look up at the night sky and see a planet, remember that it's spinning. Right now, as you watch, that world is turning. Some spin fast, some slow, some tilted, some backward. Each rotation is a story, a record of billions of years of history. And we're just beginning to read those stories. The solar system is not a static, unchanging place. It's dynamic, evolving, full of motion. Planets spinning, moons orbiting, asteroids tumbling. Everything in motion, everything with its own rhythm. And the more we learn, the more we realize how much we don't know. Why does Venus spin backward? We think it's from an impact, but we can't be sure. Why does Neptune have such fast winds? We know internal heat is involved, but the details are unclear. How stable is Earth's rotation over billions of years? We have models, but the future is uncertain. These are the questions that drive planetary science forward. Every new mission, every new observation, every new discovery brings us closer to answers. And sometimes, those answers lead to more questions. That's the nature of science. The more we learn, the more we realize how much there is to learn. But that's what makes it exciting. We're exploring, discovering, piecing together the puzzle of how the solar system works. And rotation is a crucial piece of that puzzle. It's not just a quirk or a curiosity. It's a fundamental property of planets that affects everything from climate to habitability to the evolution of life. So the next time someone asks you why planets spin differently, you'll know the answer. It's because the solar system was born in chaos. Collisions, impacts, gravitational interactions, all shaping the planets into what they are today. And that chaos is what makes the solar system interesting. It's what makes every planet unique. It's what makes exploration worthwhile. Because there's always something new to discover, always another mystery to solve. And that's the beauty of studying space. There's no end to the questions, no limit to what we can learn. Thank you for joining me on this journey through the spinning worlds of our solar system. If you enjoyed this exploration, a like or subscribe would really help the channel continue making these deep dives into the cosmos. And remember, every planet has a story written in its spin. We're learning to read those stories, one rotation at a time. Good night, and keep looking up.